It is the top of the hour, so let's get started. Welcome everybody, and thank you for joining us for the last talk in Series 1 of the IMS Virtual Distinguished Lecture webinar series. Today, we are joined by Dr. Sergio Saponara. Dr. Saponara is a full professor of electronic engineering at the University of Pisa, where he is the president of the bachelor and master's degrees in electronic engineering. He has served on the organization of more than 150 international conferences, mostly IEEE and SPIE, as well as been the guest editor of special issues in several ISI journals. Last year, he was awarded the Best Editor Award from IEEE TC VLSI. With that, I'll turn it over to Dr. Saponara.
Okay, so welcome. Can you hear me?
Yes.
I will start sharing my screen. Okay, so welcome everybody to come here. Good afternoon or good morning, depending on where you are connecting from. So I will present, thanks to the IEEE Instrumentation and Measurement Society to give me this opportunity to hold this distinguished lecture also in this pandemic era and reaching you through this webinar. And we will talk about sensing and computing system for high performance measurement with particular focus on autonomous vehicles. So thanks for the organization to provide me this nice introduction. So we will discuss the societal, economical, and technical challenge of autonomous and connected vehicles and intelligent transport system. And then we will enter more in the challenge coming from remote sensing, particularly with a focus on radar and not only on LiDAR and camera, sensing technology for navigation. We will discuss also problems coming not only from the front end and acquisition of sensors, but also from the computing needs and the fact that high performance computing will become embedded in the cars, and we will see also what is doing Europe in this field with the European Processor Initiative project. We will see also interesting parts related to also changing in arithmetic data representation, so going beyond floating points, and then I will draw some conclusion. I will try to stay in 50 minutes, so to leave 10 minutes for discussion. So, okay, sorry. So you can see also my face and not only my slides. as I say, there is a lot of time that there is innovation in the cars, but now there is a lot of interest due to the fact that there is a high economical and societal impact of this technology. Since, okay, we are discussing a lot of this COVID era, but you have to consider that every year worldwide, more than 1 million of people are killed due to accident with the cars. And in Italy is at least 10 people each day. There is also a big momentum on the Green Deal, so reducing CO2 emission. And also, you know that Dieselgate already costed a lot of billions to car makers. Also, there is a question of improving the city life conditions, so to have less pollution, less traffic jam, improving also user experience, and particularly, for example, inclusive mobility for all. So, for example, in Western Europe, North America, society is getting elder and elder, and so it's important mobility for all. And at the end, there is a lot of money that is put there due to the fact that you have 90 million of new vehicles each year. For example, 35 million of e-bikes sold each year worldwide. So there is a possibility of return on investment, since obviously this technology requires a lot of investment. The trend is that vehicles are becoming electrified, connected, and autonomous. And what is important that the technology that we will discuss today and in general for automotive then can have a spin-off in robotics and Industry 4.0. So automotive has the volume that are needed to sustain a huge investment, but then you can use it for robotics, for Industry 4.0. And indeed, you have seen that there is a sort of connectivity between semiconductor industry and ECT companies and classical vehicle manufacturers. So there are alliances between Intel, BMW, NVIDIA, Bosch, group like Volkswagen committed to invest several tens of billions of dollars for electrified and autonomous vehicles, inventing new platforms. So, and also, for example, now 5G is emerging, and for the first time in 5G, both the classical mobile connectivity, but also the connectivity of vehicle has been considered, and there is the 5G Automotive Association mixing names from the automotive industry, like, for example, BMW, Ford, and so on, tier one like Continental, but then classical, let me say, semiconductor chip provider like Intel, Huawei, and so on. And obviously, every day, we know about new companies proposing a new solution. And also, in terms of economic value, if we see a graph like this, in terms of share, still the market of integrated circuits is dominated by cellular phones, but you see automotive and Internet of Things are growing. But if you see, if in the future, which is the most promising domain on which to bet, automotive is better than cellular phones. And for example, game console is a sort of declination of the interest. So I think these numbers are important to say that there is a momentum on investing measurement technology and NCT technology on automotive. Obviously, there is a big dilemma. High-level assistance, fully autonomous. Obviously, 100% safety is not possible. So every time there are some, it happens an injury involving an autonomous car, or there is this debate. What is possible is that, thanks to technology, the statistics of incident, injured, dead people will be in favor of adopting technology. So at the end, what we are, the goal is that instead of having more than 1 million people killed, you will reduce dramatically this number. This means that the technology is good for this. And already there are action to consider the legal part, the legal issue, also the psychological issue that to adopt the technology. But I think that this will not stop the technology to be adopted. So since the problem is not having 0 incident, but if I decrease this 1 million to a level that is much below, the technology will be accepted. Obviously, the key issue for this is having robust and accurate measurement of obstacles around the vehicle, of the environment, of the status also, or the driver, of the car dynamic and position. Just to say that is worldwide in Tuscany, that since University of Pisa is based in Italy, in particular in the Tuscany region, is not only is famous Tuscany for Leonardo da Vinci and Galileo Galilei, and obviously there are also, these activities are also the results of collaboration with many companies that are invested in an area, this is less than 5 kilometers of the sides, and also invest in big company like Intel, recently Huawei, Apple, or more traditional automotive makers like Vitesco Technology from Continental, Magna, Pierburg. Maybe you know the Piaggio brand for the scooter. So, okay. Coming back to the technology point, so the idea is that the vehicles in the car will become a platform now to bring a lot of different type of sensors on it. And obviously the goal is not only having the sensor, but then having also the acquisition and processing technology to understand which are the obstacles that are around the car, where they are positioned, and which is the direction and the relative speed with respect to my vehicle. And obviously the problem is also the confidence that I have with these with the results of this measure. So it's important not only performance in terms of range, resolution, and accuracy, but also how reliable are these acquisition. So concept of uncertainty, of repeatability, but also when I start putting a lot of technology on the car, maybe using V2X, so vehicle to everything connectivity, there are also problems of confidentiality, of trustness, of identification. So there is also a problem of security. So when I speak here of sensing, it's not only the problem of the physical sensor, but I consider the whole chain involving the sensor, the acquisition front end, all the technology for processing and understanding of the data. So obviously I come from Italy. I put a nice Alfa Romeo red Stelvio here, but if you look at a presentation coming from maybe professor from Germany, will put a German car. So the vehicle is becoming a platform for the pervasive use of the technology of the instrumentation and of interest for the instrumentation measurement society. So in this moment, there is a lot of research on radio frequency and millimeter wave technology for millimeter wave radars, connectivity based on both direct short range technology like VLAN for cars, or cellular based 5G, obviously satellite technology. Then a lot of technology and research on sensor signal processing, where with respect to the classical sensor like Hall sensor, pressure, strain gauge, and so on, here the challenge is managing in an effective way high bandwidth sensors like cameras, radars, lidars, high performance inertial measurement unit, and also making a gain from fusing of this data and operating real time. Obviously, the sensor technology is important, and here the challenge is try to exploit a micro electromechanical system or a micro opto electromechanical system to achieve compact solutions, since obviously what differentiate automotive from, for example, industry technology, and in the cars you need also to have compact solution, since the size of the car is limited, while in an industrial plant maybe you are less exposed to request on low sides and on low weight. Then, as I said, there is a lot of pressure on predictive diagnostics, since we are putting technology, but we want a technology that is secure, that is safe. I can predict if there are failures. So a lot of research on how to predict that there will be a failure. And obviously, to manage this huge amount of data, you need embedded high performance computing. So you will need a lot of memory, multi-core processor, on board your car. And the challenging here that you need high performance computing, but at the same time you need security, you need safety, and you need a price that should be competitive for a large volume production. So a lot of interest from a societal and from an economical point of view, but also a lot of challenge to be addressed. So So a lot of work for industry and for researcher. So this is, for example, already if you took a premium car today, there is already a lot of sensor mounted on that for context awareness. And for the moment, we will focalize the next slides on radar. Then you say there is a mixture of ultrasonics sensors, camera in the visible, or particularly if this is a premium car in night domain, and different type of radars. As I said, the challenge are also related to processing this data, and so there is a lot of investment on understanding technology. So AI, the use of AI technology for image classification and understanding is entering the domain. So you have several streams. There is classical processing based on initial raw data, raw image processing for pre-processing shape detection, but then for the classification, for the understanding, to understand that here you cannot turn on the right, or if you have a speed limit, then you need classification algorithms. And here there is a lot of research on AI-based technology. Then, and I will have some slides focused on this, one of the technology that is gaining momentum is radar. Since camera are okay, but it's difficult with the camera to understand in real time relative distance or relative speed, and also if you have bad light or weather condition can get a problem. LiDAR, we will see, are still costly. For example, Elon Musk say that he will never put a LiDAR on his Tesla. So a technology that is mature and has a cost that can be used to combine with camera is the radar. But here, the evolution of radar is thanks to the evolution of the basic electronic technology that allows us to work at very high frequency, 77 gigahertz, with a low-cost solution. So this is an exploitation of the third generation long-range radar from Bosch. Bosch is already arrived at fourth generation. Obviously, available data publication, you can find this one. And as we'll see, there is a combination, a lot of technology, since you will have a millimeter wave board with patch antenna realized on the board and silicon germanium chipset. In this case, it's from Infineon, but anyway, you can have from several companies like, for example, STMicroelectronics, TI, and so on. Then a sort of motherboard equipped with the basic processing and connectivity through the in-vehicle network, that can be a CAN or FlexRay, or in the future, Ethernet. And also packaging is important. For example, here, the package of this radar is done so that this is at the same time a package, but this is also create a reflecting effect, so increase the gain of the antenna. So a lot of technology that allows you to have a sensor that can give a measure of distance, presence of a target, relative distance, and also direction of arrival. We will detail this in next slides. Then a lot of research is also on technology for also biometric measurements, since a lot of accidents are due also to, for example, fatigue status of the drivers. And one of the problems is making contactless measurement of the status, if it is fatigue or not, of the driver, since obviously no one wants to have electrode on it. And for example, there are technology based on using the camera mounted on the rear mirror to analyze the face, and according to the frequency of closing and opening of the eyes, you can estimate the status, if it is fatigued or not, of the driver. Also, there can be low power radar embedded, and there are a lot of works published on transaction instrumentation and measurements. For example, in the wheel, where you exploit the fact that the heart and the chest are moving when you are braking or due to the heartbeats, and this can be measured with contactless with the low power radar. Or this is a solution from Texas Instruments, but there are several of them available in the market from several companies. For example, with embedding some capacitive sensors in the wheel, you can measure the galvanic skin response. So then thanks to a fusion of data from the galvanic skin response, heart rate and breath rate, and face analysis, you can have on board a measure of the status of the driver, and so you can avoid a lot of problems coming due to errors of the driver. Obviously, up to now we discussed mainly of new sensor or new technology to processing the data of this sensor. Obviously, putting a lot of this technology on board create also a networking problem. So there is also a lot of research on how to make a network, a reliable network in a closed environment, in a short, small environment, avoiding electromagnetics. And so you had several evolution from very low speed bus like LIN, local interconnected network, to the basic CAN, to FlexRay, and now the challenge is represented by bringing Ethernet on board the car with the automotive Ethernet is the next domain. And also there is a lot of activities on the chip also design, since for example, this is the snapshot published from a paper from a driver from FlexRay. You, for example, you have to face a very extended temperature range, -40 to 150, large bus voltages. This is up to 58 volt in a car equipped with the 12 volt battery. So imagine what happened in a car equipped, for example, with 800 volt DC bus like the last Porsche Taycan. Also there is a lot of trend towards the integration of analog and digital processing, and so there are several examples of companies providing an integrated solution where you have a configurable and generic sensor interface, so the same chip can be used to address the processing and acquisition need of several temperature, speed, pressure, accelerator sensors, and on board the chip, you have both the analog interface, but also you have processors, you have already digital signal processing. So let me say the intelligence, the data processing, the data mining is moving near the sensor, no? And so you have a smart sensor solution that can be networked. And even more complex, this is an example of a collaboration that in PISA we have with the Massachusetts Institute of Technology with Professor Kirtley. Here, for example, other challenge come from the fact that this is example a bell starter a 48 volt bell starter generator. The control electronics, the intelligence with the sensors and actuators is integrated in the machine, near the machine, in the same package. So you have a smart electric machine, and this obviously for all the type of sensor. This is the schematic that are needed to measure phases, position of the stators, of the rotors, current, and so on. All these kind of sensors are placed near a very harsh environments in terms of vibration, in terms of electromagnetic interference, and also there are this kind of challenge that the sensor and the sensor processing for automotive has to face a very harsh environment. And so, for example, electromagnetic compatibility interference should be one of the key functional points of this analysis. Obviously, as I say, further challenges are coming not only from the fact that cars are becoming autonomous, but also by the fact that cars are becoming electrified. So, for example, there is a huge, there are huge investment on sensors and sensing technology for the batteries to also estimate the state of charge, state of health status. And we are going from state-of-art solution where, for example, this is a pouch cell is connected locally with the sensor measuring, for example, deformation, temperature with thermistor, or maybe there are all sensors and so on. But there are also propositions in literature, and there is a lot of research on this, for example, exploiting optical fibers, so through the fiber Bragg grating sensor, to have a distributed measure in a battery pack of strain, temperature, pressure. And obviously here, there is a lot of challenges since, for example, silicon photonics is entering as a new technology for integration. Now it's still costly, but there is a lot of research on this, and maybe how to have to minimize the size and the cost of also the reading electronic, in such case, optical interrogators. So these are new trends that we are touching in our university related to new sensing technologies for automotive. As I said in the introduction, the problem is not only making measurement, but is also, and I will treat this, a lot of interest on high performance computing, since obviously moving from safe driving, maybe based on electromechanical passive system, to self-driving, the needs of computation on board goes from tens to hundreds of mega instruction per second to one or several tens or hundreds of tera operation per second. These are the performance claimed by recent platforms from NVIDIA, or for example, the full self-driving onboard computer from Tesla that claims more than 100 tera operation per second. And all, as I said, has to be done following strict requirements in terms of safety that is standardized, that should follow normative like the ISO 26262 with stringent requirements in terms of safety integrity level, where a SIL D requires that you have to guarantee that more than 99% of faults are detected, and the failure in time, one failure in time is one failure each 10 elevated 9 hour. You know, your failure should be less than this. And already now we are speaking not only of fault tolerant, but we have to guarantee that also in case of failure, an operation is done as concluded. So it's not only the problem of detecting failure, but also to manage them in a way that you guarantee the safety of the mission also in case of a failure. So this is to show now the opportunity that we have and a lot of research field that we have. Now I will touch very rapidly some results that we achieved in the above domain. Is not closing them, but is just to show some practical results. So for example, for context awareness, so the challenge is fusing data that come from sensor like ultrasound sensor, lidars, camera, radar, plus information coming from also connectivity, so V2X, V2V, so and also the availability of maps. And then it's important not only the acquisition, but then fusion of information, and thanks to AI, also making a planning, making a decision. This obviously to sustain an evolution from the absence of assistance to highly assisted driving to full autonomous driving. Now maybe we are in, if you buy a premium car between 2 or 3, the challenge is going from to 4 and 5. Obviously, if you go to 4 and 5 with vehicles, then you have the technology that can serve robots, drone, and so on. So again, the technology that we are discussing can have a spin-off in robotics industry 4.0. So for context awareness, vehicle perception, maybe there is a lot of discussion on a mix of 3 different types of sensor. So obviously cameras that are available, are cheap, are available at low cost, maybe using both visible infrared camera due to the fact for night vision. This is already available. This is an example of a system we developed at the University of Pisa, where for traffic and road sign detection, where you acquire data and then was published 4 years ago. So it's a technology that is mature, and thanks to FPGA-based processing, you can recognize traffic and road sign thanks to shape and color analysis, and then give support to the driver. The problem of camera is that in harsh condition, it's difficult to detect objects, and maybe also to automatically say which is the relative distance and speed. This is why it's getting a lot of momentum. Radar, that I called it as a master of motion measures, that allow measurement in harsh condition, can allow also with the limited power of the radar available in the market for automotive are less than 10 milliwatt and can reach 200 meters thanks to also a focalized antenna. The problem of radar is that you can have a limit in, it's difficult to go to an accuracy less than 10 centimeter. And obviously this is why someone is proposing LiDAR. Here there is a debate since, for example, Tesla is betting on a mixture of radar camera, avoiding LiDAR. LiDAR is still costly as a solution, but for example, Google with its company Waymo is betting on it to achieve a very centimeter accuracy and to drive really full autonomous car. This is an example of a LiDAR, so it's a technology that is available from Velodyne, that is a US company. The problem, I go directly here, is still for the moment the cost. So there is a lot of research on this. This is an example of also fusion of companies that has been created to reduce the cost of the LiDARs. Maybe these are prices that are already available in the market. These are target prices. Obviously here, there is a lot of contribution. Here the challenge is really reducing the cost of LiDAR that come from the adoption of a micro-opto electromechanical system. Since obviously, if I reduce the cost of scanning, maybe the number of array of lasers transmitter and receiver, maybe I can reduce this cost. And this is why, for example, in our university, in collaboration with a group of Professor Nannini, that unfortunately disappeared a few months ago, and Francesco Pieri, we made some research on how to have a micro-opto electromechanical system to have a single laser, and then using this controlled mirror technology, make the scanning to reduce the cost. Since here, as I said, the real challenge is having LiDAR at the $100 cost, so a price comparable with the radar one. Radar instead, as I said, this is technology available. This is an example. This was done in a collaboration between University of Pisa and in two different projects, with the CNIT RAS for maritime application and with EDS, that is a company operating in Pisa related to railway crossing safety distance. And here, for example, the idea is that with the network of radar, you can create a smart infrastructure. So these were radars done to make a smart infrastructure, not to be mounted on the vehicle. Obviously, since you reduce the field of view to increase the gain of the antenna, if you want to have a all-around view coverage, then you need to connect them in a network. And most of radar today are based on a frequency modulated continuous wave approach, where the transmitter span, or this radar were done in X-band, so around 10 gigahertz. Automotive radar typically done at higher frequency, around 77 gigahertz. You span the frequency, you transmit the signal, the black one. When this goes to a target, there is an echo. If there is a distance, there is a time of flight. So you see that the signal, the red signal, comes back with a shift in time. And if there is a difference in the relative speed, there will be Doppler effect. So there will be also a frequency shift due to Doppler effect. So mixing the two approaches, you have the same signal that is delayed in time and shifted in frequency. By analyzing, so here you have the received signal and the transmitted one, by analyzing the bottoming frequency after the mixer, typically in a digital domain, from this signal, you can extract information on if there is a target, which is the relative speed, which is the relative distance. Obviously, to solve the direction of arrival, you will need multiple receiver. At least you need 2 receivers for each plane. So for azimuth and elevation, you need at least minimum 3 signals. And what we have seen that using COTS components, so these radar were designed not developing new semiconductor technology, but mainly reusing components available in the market, and then designing microwave board with a limited power of 10 dB, you can reach a distance of 300 meters. With increasing this with an external power amplifier up to a pair of watt, you can reach distances up to a pair of kilometers. These are, for example, example of antenna, resonating antenna designed by the group of University of Pisa of Professor Monorchio. These are example of microwave boards with the COTS LNA. The processing, as I said, was done. Front end was in an analog domain, but the back end was in the digital domain and was based on multi-dimension fast Fourier transform to analyzing the frequency domain, the peaks, and then analyze where is the target. The design of this part was done on FPGA to achieve real time, but at low power cost, with classical, let me say, HDL design of the blocks. So this is something that for groups designing integrated circuits is straightforward. And for example, even using low cost solution, these are products from Xilinx, but you can use FPGA from Intel Altera or whatever, you can achieve the processing in real time of multiple channels. Obviously, you can bring these also on programmable core. In such cases, maybe the power consumption will be higher. Obviously, there are also a lot of interest, for example, for the new generation of microcontroller Haurix from Infineon will be equipped also for radar processing embedded in the micro. So also there will be the new generation of microcontroller due to the increase of interest for the use of radar will be equipped also with dedicated unit for radar processing. And this was designed and tested in experimental trials done in front of the bay of the Naval Academy in Leghorn, near Pisa. And for example, this is the antenna that I showed before. So the system, so one transmitting antenna, 3 receiving antenna, was tested in the configuration of some watts to reach up to 2 kilometers. The targets in some cases were ships of different shape, also different materials. And these are the kind of images that you can get in terms, obviously from the radar, you cannot see shapes or colors. You see a map that automatically gives you the intensity of the peaks with respect to the background, so you have information on the distance and on the relative speed. No? And depending if the speed is positive or negative, it is coming near you or is going far from you. So maybe mixing low-cost radar with camera, then you can use the radar to detect the obstacles, maybe which is the relative speed and distance. And when you have detected, then maybe you can use the camera to classify them, since you can say, okay, this maybe is wooden, this maybe is another is iron, since also from the color, from the shape, you can understand the type of, if it is a civil ship, is a military ship or not. The same concept, I will go fast, has been used also for other applications. So not only this was an application for, let me say, small bay control, so to cover a small harbor, ingress and outgress of ships from the bay. But the same can be used, for example, for monitoring a railroad crossing or maybe road crossing. This was done, a similar concept, from a radar from this company, Ingegneria dei Sistemi, and was equipped for radar to monitor, for example, a road crossing in near Cremona in Pianura Padana, which is a very dense area with a lot of cars, but also a lot of fogs. And so to increase the safety of the infrastructure, and so to automatically check if there is an accident, and then through a V2X technology inform arriving car and avoiding to create a chain of injured people. And this is, for example, again, images that you can use. For example, this was a test that we have done on a parking area where instead the radar was configured with maximum few milliwatt of transmitted power. So a range was reduced from 2 kilometers from here to less than 200 meters here. And again, you have images when you have range and relative speed of vehicle or pedestrian. Obviously, here it's difficult to recognize. This was a mix of biker vehicle, and it's difficult to recognize which is the bike, which is the vehicle. That maybe this is why I say that you have to use in combination with a camera. With the camera, then you can classify your object. And obviously, at the end of this presentation, I put also a bibliography where you can find a lot of review of presented technology for radar. Another challenge is related to sensing technology for navigation, since obviously here the aim is paying the cost of accelerators and the gyro used in consumer, maybe the one that you have in your Nintendo, try to use these to make an autonomous car. The problem is that if just using gyroscope and then accelerometer at low cost for the consumer world, just using them, and there is a lot of research on this from several companies. The problem is that due to the problem of bias that you have in the accelerator and the gyro, for the consumer, after 10 second of integration, you have errors that are not acceptable. So best case, you will reach 1/4 meter of error for autonomous cars. And also just increasing the measures does not improve the situation, since it's been demonstrated that accelerators and gyro are affected that bias instability. So for some time increasing the measure and then integrating reduce the error, but then going more than 1 second starts creating a long-term instability. So the solution is mixing inertial measurement with satellite signal, and particularly the idea is using real-time kinematic technology, where, for example, in a covered area, so you need the help of the infrastructure, maybe your car is getting the signal for your Galileo or GPS satellite, plus from a radio signal, the information of the position of a known point. So this should be part of the smart infrastructure. So using the IMU, plus using the inertial measurement unit on board, plus making a differential analysis of the satellite signal received directly and the satellite information received from a known point from which is known where it's placed, you can correct with algorithms on board and improve the positioning. And this has been implemented with a company, Pure Power Controlled, based in near Pisa. The system, okay, from an algorithmic point of view is there. Obviously, there can be space for optimization in terms of technology, since it was built from COTS technology. And there will made tests in this, for example, is an industrial area where, for example, this can be used for a vehicle to support warehouses, or, for example, industrial vehicle. And the two traces compare the results in the accuracy in positioning and navigation. The red one that you have mixing inertial sensing, satellite sensing with Kalman filtering, and the other instead of just using satellites. And you see that you tremendously can reduce errors and improve the accuracy. So this is another challenge, how mixing different type of sensors, so inertial measurement, have global signaling, instead of paying a lot for very accurate gyroscope or accelerometer, but just use consumer one, but mixing with estimation done with Kalman filtering and satellite signal, you can improve, achieve the right trade-off between accuracy and price. Obviously, companies are still working on, company like STMicro, Bosch, Invent Sense, Analog Devices, on improving MEMS technology to achieve better accuracy, less bias at the price of consumer sensor. As I said, and this is this can be not possible if you do not have, equip your car with embedded high performance computing. This is why there is this initiative, European Processor Initiative, that is mixing a lot of partners mixing. So let me say, partners coming from the automotive world like BMW, Infineon, ST, Electrobit, and so on, with partner coming from the HPC world like Atos, and new company have been founded like Cypel, plus the support of several other university research center, to bring also in Europe a solution for high performance computing on board the car. Obviously, this slide are just this project is ongoing. The goal is let me say, developing technology This is a roadmap where there will be a first generation of this REA processor in 2021, 2022, and then new generation. And this will be equipped with a multi-core ARM solution realized in very scale technology. 6 nanometer technology is the ARM with 64-bit, but maybe enhanced also by other European IP that can come from embedded FPGA or massive parallel processor array, in such cases from Calray, that is a French company, or for example, a RISC-V based accelerator coming from a group led by Barcelona Supercomputing, plus, for example, dedicated solution for security, since obviously security is important, with the hardware and software dedicated solution coming from University of Pisa and in collaboration with Provarran. And again, this is due to the fact that you have to face what I discussed before. You need high performance computing on board, also with the capability of managing a lot of data, since this is data coming from Intel, where for autonomous vehicle is estimated a consumption of 4 terabytes of data per day. No? So really, oil is the new oil are the data. Okay, just before concluding, last results from a research activities, a small exploration activity that you have done in University of Pisa, is that due to the increase of interest in machine learning, AI for classification, there is also a debate on how to go beyond the classical integer and floating point data format. This is also searched by industry. So, for example, if you see last product from NVIDIA, Tesla, full self-driving chip, Intel, they are betting on new formats that at the end are or you just using integer or using a sort of floating point 16-bit. And to face this, so the challenge here is to reduce the size of the format, but particularly for AI application, for classification, achieve the same accuracy of floating, since when you go to integer, typically you reduce the size. So there have been proposed this new format called POSIT. You can find a lot of literature there. Is a sort of compressed format of floating. And okay, in PISA, in the public, you can read the publication. We are proposing a sort of smart implementation of POSIT, so hierarchical approach where you have not to interpret every time the POSIT format, but you can also make some manipulation directly on the initial format. So we have a hierarchy of 4 different types of operation. This can be implemented. We have a software library implementing it, or you can implement also via through an hardware accelerator, so a coprocessor. And we demonstrated that, for example, applied to classic machine learning algorithm like k-nearest neighbor, you can achieve the same accuracy of using float, but reducing at least by a factor of 2 the complexity, since POSIT 8 is better in accuracy than float 16, or POSIT 16 is equal to float 32. We implemented also AI application, and here at least POSIT 8 can achieve roughly the same accuracy of floating point 32. That means that you reduce by a factor of 4 the complexity, so improve, reduce cache misses, improve, reduce the cost of data transfer. So really important to implement large neural network on embedded system. And for example, we proved also both on ARM SVE or RISC-V with vector extension platform, and we proved that this is a real interesting approach. So this is, for example, another field of research, new type of arithmetics to have efficient implementation of AI on embedded part. So to conclude, since we ended the time available, so the field of smart vehicle and intelligent transport system is a huge R&D field for instrumentation and measurement. We have seen several possible challenges to be addressed, and so there will be for sure a lot of interest both in the research field and industrial field. So let me say, I hope that the community of instruction and measurement can contribute with needs in terms not only on the sensing technology, but also on the signal processing part, on the A part, and on the system view that is typical of the instrumentation and measurement. Thanks, and here I reported the bibliography of what produced in the last years to have more details of what I presented. So thanks for your attention, and we start the question and answer session if there are. Okay, so looking to the question and answer, I see that there is a question relative to is there is a time synchronization challenge that must be met to make this all work. Obviously, when we have, for example, the different problems of fusion of data that can be related to navigation, so mixing EMU and satellite, but the same can be also when I have to fuse for context awareness the same scene observed by a camera and a radar. Obviously, you have a synchronization issue in terms of time of challenge, and so also there is a research in how to keep let me say, the latency and so achieve synchronization within a certain field. And the idea is also making some algorithm there to make this robust. The trend here is working a lot on more on algorithmic side and try to let me say, reduce the requirements on the hardware, since obviously the hardware, the technology, if you are requesting too much performance, increasing the cost, and have we seen that the automotive instead is requiring low prices on a large volume. Okay. I don't know if there are other questions. What type of latency is allowed into end links? This is a really interesting question, and this is due to the fact that, as I said, when I speak about BOF for the direct short-range connectivity and cellular connectivity. Obviously, for safety-critical application, really, you need to go to, let me say, latency in the order of milliseconds. This is why I believe in the coexistence of both the cellular V2X, but also direct connection, since the cellular V2X connectivity, due to the conflict that you can have accessing the network, maybe cannot guarantee this, due to the fact also that I believe on embedded high performance computing, since you cannot, for a safety critical application, rely on the fact that you ask an AI network solved by a cloud and then you give back the response, but due to the problem that you, for robustness, you can lose the link, or you need low latency, you need to calculate to make the understanding of the scene on board the car. This is why you need embedded high performance computing. And I believe here, okay, V2X can be an help, but you cannot rely that all the intelligence is outside the car, but has to be on the car to keep low latency and also failures of the links. Another question is related to COTS used in the final client application or only in laboratory. Obviously, we are a university collaborating with industry, so then the exploitation is done by industry. So for example, the European Processor Initiative, one of the results was the creation of a new company, Cyper, that will try to bring the research on the market. But obviously, as a university, typically we end at TRL that can be high, but is not directly on the market. Typically, then we collaborate or with other companies or with the spin-off created, not in the autonomous field, but for example, in space, with some colleague, we created a company called Ingenieurs that is bringing technology to the market for space. Okay, other question. It's possible to perform some kind of valuable research in this field, even in the case a lab does not have complex or expensive instrumentation. I see many collaboration with company. Okay, my feeling is that there is a lot of opportunity for research, also theoretic research, since, for example, all the stuff related to data fusion, for sure you need to develop new algorithms, new technology, and you can then also based on simulating environment. So I think that obviously the collaboration with industry is important, particularly, obviously, I'm teaching, I'm a professor of engineering, to give real challenge. But I think that you can do research in the automotive field also without having complex and costly testing infrastructure. Since, as I said, a lot of problems, for example, now we discussed the synchronization problem, networks, research on algorithms. This is something that you can solve also with needs a solid theoretic basis, a solid also simulating environment, and maybe still in the lab you can try to recreate and you can test a lot on embedded systems. So my feeling is that there is a space for research also if you don't have directly a collaboration with the big automotive industry. We have time, okay, for other questions. So how about radar blind speed when the target cannot be measured by radar? As I said, no, I'm not proposing radar as a single solution. No, I believe in what I presented is in a mixture of different kind of technology. So the achieve full autonomous capability in every conditions, since this is the challenge, then you will need a mix of onboard sensor, ultrasonics are already there, camera already there, so you can have radar, the availability of maps, the availability of V2X technology. So for example, a vehicle can communicate with another vehicle, or thanks to 5G, you can detect the people that are around you. Like, for example, if you have an Apple, you can see how many friends are around. So I believe in a mixture of the technology to achieve this context awareness with high confidentiality in every condition, not only on the radar. What are the key considerations in the fusion process for security and privacy? Then obviously I will touch, since obviously the talk is limited to 45-50 minutes, less this problem. Obviously, security and privacy is something that is increasing as an issue. And the more and more we put, obviously, new technology, we put V2X, we increase the surface attack. We increase also also through cloud. There is the problem of confidentiality. So it's something that needs also there a lot of research that we are doing. I've not presented the detail, and this is typically done both at hardware level, where typically now every microcontroller processor is equipped with an hardware security module. So for example, in EPI, the Aurix safe and secure processor from Infineon or the future REA processor will have hardware security unit on board to have advanced techniques for data root of trust, for data security, but also there is a lot of research on new, for example, algorithms. For example, we are doing in Pisa, thanks with the collaboration with the group of Professor Gianluca Dini, activities on secure over-the-air update of the software, since obviously all these kind of technology that you have are software-based. You can re-update the software remotely, but then if you do this, there is a problem of the security and consistency and privacy. So there is a lot of activity there. Indeed, for example, at University of Pisa this year, thanks also to the interest of the director, was a collaboration between our department and the Department of Computer Science, has been created a new master degree in cybersecurity to address also at the education level the fact that cybersecurity is a dominating technology both on hardware and software aspects. Okay. So I think that we are ending the time, but I was able, I open in a clear way to address all your question, your nice question. If you have other or you want to replicate, I'm here. I think still we have a few minutes available. Obviously, then if you are interested, since obviously it's difficult to compress in a few minutes all the discussion, maybe you have my reference so you can contact me. So I thanks Instrumentation and Measurement for this opportunity. I put also a link on a video that was realized thanks to support of University of Pisa. And for European Processor Initiative, obviously you can make a type on the web, and there is a very nice website and extra information. So for any question that you can have further, I'm here and I'm happy, you know, to make a network and to discuss these points.
Thank you so much, Dr. Saponara. That was wonderful. And thank you to all of you for attending both on Zoom and on Facebook. We'll conclude here.
Okay, so thank you very much to all of you. I hope that this 1 hour was not wasted and was interesting for me. If it was interesting, I hope was interesting also for you. And thanks again to the IEEE Instrumentation and Measurement Society to give us this opportunity also in the pandemic era, to have this webinar and this lecture. Okay, thank you.